So I'm born and raised overseas, but roughly in the equivalent of my high school, or more like maybe junior college, I got fascinated by chemistry. So when I went to university, I wanted to study chemistry. Chose analytical chemistry, which is a really peculiar field, given kind of the precision in thinking and skepticism that comes with analytical chemistry. It's kind of interesting world to be exposed to. Then I got interested in biochemistry. And what maybe had the biggest impact on me early in my career was to work in a lab during summers. And I worked on isolating enzymes from the heart in rats and do some enzyme assays. And I was just fascinated by this, that you could basically sacrifice an animal and within a minute have a tissue ground up in a beaker where you could measure basically oxidation, just like with a DO probe, but you would just measure the activity of the enzyme. You could change this, you could change that, and I could produce these double reciprocal plots and all these things that you learn about in enzymology, and I was just fascinated by this. Then I started thinking, okay, now I need to do another enzyme. Then I realized, there are quite a few other enzymes. There are a lot of other enzymes. Which one do I choose? And I realized that as interesting as enzymes are, they're basically catalysts. They tell you what reaction is being accelerated. They don't tell you that much about the nature of the living process, which is what I was interested in. And I realized there are hundreds, maybe thousands of these that come together basically as a system to produce, the function of a cell. So that realization really led me to seek an educational path that allowed me to do the chemistry or the biochemistry as well as system science or systems analysis. And I discovered that chemical engineering allows that. So chemical engineering as a field is about processing petrochemicals, big systems, very sophisticated system science and control theory that goes with that. But they were also, at that time, applying chemical engineering principles to bioprocessing and understanding cells. And so these two things were found in a chemical engineering curriculum. So that's how I ended up going to graduate school in chemical engineering. Came out of chemistry, biochemistry, learned all my mathematics and all that stuff, and went into chemical engineering. Basically, at this point in my career, I had learned a lot of chemistry, a lot of instrumentation. I'd learned biochemistry. I just loved biochemistry. A lot of fun, proteins, catalysis, DNA, and all this stuff. I learned a lot about system science, linear algebra, constraint-based optimization, multidimensional calculus, and I was programming all night. Back then, you worked on mainframes. Personal computers came on the market when I was in graduate school. But before that, we all stayed in the computer center all night to program and do calculations. At the point in my career when I had my PhD, I was very fortunate to know all these disciplines. And we know in today's world, to function well, you really need to be interdisciplinary. You really need to know many disciplines. And I was just lucky that my path kind of took me through all these disciplines. I could learn that skill set that I mentioned. I did not know biology in detail. I didn't have a good feel for biology. And that I acquired after I became faculty member. So when I became faculty member at the University of Michigan, therapeutic protein was coming on the market. And there was a company that actually came out of UCSD. This would have been probably late 80s, called Hybrid Tech, about hybridomas to make monoclonal antibodies. You have to look up the dates, I can't remember them exactly. And the company was bought by Eli Lilly for $50 million, which at that time was like, what? I mean, that was like the biggest jackpot you ever heard of at that time. And that was actually the nucleating event for the biotech industry in San Diego, as it turns out. the people that were successful at that, some of them started venture funds, started other companies, and success breeds success, and that's kind of the defining event of the biotech industry in San Diego, as I learned much later after I moved here. But I started working with these hybridoma cells, which were fusions of B-cell lymphomas, B-cells that actually make the antibody, and lymphomas that are continuous cell lines. You could fuse them together, you get a hybrid cell that both make the antibody and grew like cancer. And these were the production vehicles, the cell lines that were used at the time. So I started growing these. I'd never grown anything, in a lab as a graduate student. So I had to learn on the job as a professor how to run a cell culture lab. And we were successful at that. And that led me to establish contact with hematology, where they wanted to grow primary bone marrow cells for transplantation purposes. And we started working with what are now called adult hematopoietic stem cells. So we actually were one of the earliest groups dealing with adult stem cells. And since I was in an engineering school, they were MDs, there was this big problem, practical problem of bone marrow transplantation. And we had this unique combination of being able to have culture systems that called for all sorts of engineering, oxygenation, fluid flow, and very delicate and intricate cell biology. We actually combined those two things to meet this need of producing cells for transplantation. And that simple need, so this pull from the market, helped us at that time to start a company that got funded. It's a long story, how that got funded, an interesting story. That eventually went public on NASDAQ in 1997. Was, I believe, the first stem cell company that achieved that level of success, and is still listed on NASDAQ. So going through that process, you ask about learning on the job. I learned how to deal with investors, intellectual property, real product development, because these were FDA-approved devices. How to deal with consultants, how to build organizations. It was a remarkably useful experience. So I was very thankful for that. So that's how I kind of got into the tech transfer business and building companies. And since then I've done many other companies. But I guess if you were to think about the lessons there, merging disciplines, working with creative people at the cutting edge of their discipline, and identifying a market need that at that time was bone marrow transplantation, that was developing rapidly as a therapeutic modality, all came together to give me this tremendous experience I had there. And also just the excitement of taking a company public is exciting, I came here in '95, joined this bioengineering department. I believe I was the 7th professor in the department. Now we are 25 or something like this. Yeah. And the month after I resigned my position from the University of Michigan and accepted a position at UCSD, the first genome sequence came out. And yes, and I had accepted a job here to do tissue engineering, more bone marrow transplantation stuff, do tissue engineering, regenerative medicine sort of work. And when the sequence came out, I looked at it, and I still remember opening that fold-out in that copy of Science. I said, no way, we have all the genes here. Because before then we were trying to build mathematical models of cells, and we never knew what to include and what not to include, or something missing. Here all of a sudden there was closure. Here's the whole genome, here are all the genes. We didn't know all the functions, but at least they were all there. And that basically led me to start to build these genome scale models, where I finally got all the enzymes together. I had been dreaming about this undergraduate. I had definitions of all of them there. And we started building genome scale models, and we've been doing that now for, close to 20 years. With the sort of results that some of you are familiar with. Technical education is extraordinarily important these days. Extraordinarily important. So I happen to know the gentleman that took over as CEO of Qualcomm last December for, kind of socially was an acquaintance. He got his PhD in '92 at the University of Michigan and so forth. So I went over to Qualcomm the other day to talk to him, and he said 80% of our staff are engineers. 3/4 of those are software engineers, meaning people that deal with software programming, algorithms, data, implementation, networks, and things like that. And the other balance is more, I think, materials, maybe chemical engineering, and so forth. But Qualcomm is one of these companies of the future. 80% of the staff is engineering.
Yeah.
So, I mean, it's the right thing to be doing at the moment. The second thing I think is important to realize is that we are now in the era of big data. I mean, again, going back to my laboratory experiments, I had 8 data points. That took me a week to generate. Now we'll be studying and modeling it back and forth, but 8 data points. Now we are in an era of incredible flow of information that is given due to biosensors. You can just monitor everything around you. As you know, you can put monitors in your refrigerator, be checking it on your cell phone. This data is coming from everywhere, just flowing. And it's not just financial data that the way it used to be. And now, of course, the social media people are looking at. You can be tracked where you are, your spending habits, everything. In biology, we're sequencing genomes. I mean, there's so much data flowing everywhere. Being comfortable with big data, I think that's very important. I think so. Another thing I've learned in starting these companies that I have, I've seen that people go through multiple careers very quickly after they graduate. Most people will have a technical track that is maybe less than 4 or 5 years. Then they have to go do something else. It may be marketing, it may be personnel management, who knows what it is. So adaptability and being versatile is very important. Not that you don't have to know your fundamentals well, and comfort with data and so forth. You need to be kind of open-minded or vigilant, looking around you, because you will go through multiple changes in your career. And getting a bachelor's degree at a good university like UCSD is the first step in career development. It's not the last, it's just the first. There'll be many, many steps after that, so it's important kind of to think about that ahead of time. I believe more in human capital, in people than physical resources. And I knew bioengineering was part of the future, and this was the department of 7 people, all very good. I left what was a top 5 engineering school at the time to go to a school that was maybe top 40, if ranked at all, in the mid-90s. But it was just somehow my gut sense that was the right thing to do. The field was growing, the people were right, and so forth. So there's no real magical formula for those kind of decisions, I think. Well, I think advanced education is becoming more and more important, and master's degrees in most of the engineering disciplines are advantageous over having a bachelor's degree. The only exception is probably chemical engineering, but they either hire bachelor's or PhDs. And as you may know, in some areas of chemical engineering, like petroleum engineering, starting salaries are pretty nice. Over 100 grand in some cases. So I think, aside from chemie kind of maybe being an exception, I think doing a master's degree that takes a year and a half to do, maybe a year and a half, is probably not a bad option, broadly speaking. Higher advanced education, higher degrees, advanced degrees, they tend to accelerate your career development after you leave. Now, academia versus industry is something that really doesn't come up until you get a PhD, right? So if you're going to a PhD program, you have those choices to make. But there aren't just 2 career choices when you get a PhD or a master's degree. People often go into patent law, for instance. They get a master's degree and go into patent law. Of course, many people go into medical school. People go into scientific editing. One student that came out of his PhD in bioengineering went into a financial services type company that was looking for outliers in data sets. In other words, fraudulent use of credit cards. They leverage that way. So that's maybe another piece of advice, is that not to be too confined in your thinking with respect to what your career path is going to look like. If you get a good, solid, general technical education of the sort we were talking about before, you may be surprised by what kind of career choices you actually end up pursuing. Once you're in a company, what you look for in a CV is very different of what you think academically. People think about GPAs, did you take, Calc 3 or something like that. But when you're interviewing people for position, you just look for skill sets. What can this person do if I hire them? So therefore, it's I think, essential for everybody as an undergraduate to get some research experience, some project execution experience, and so forth. You've written a program that does something like in 123, I emphasize that you can put that on your CV. I built a dynamic simulator of a cell that has well over 100 state variables. I mean, that's like a real skill set. You get hired somewhere and say, oh, this guy can do this for the day they walk in. Or you could work in a lab and know how to run an HPLC or sequence DNA or something like that. Those skill sets are very important and give you an advantage when you're looking for a job. Another thing that you all will benefit from is the fact that you'll have leadership skills on your CV. You ran this organization, you came out and did this interview, you're trying to help others, you're proactive, you probably have to manage a little budget, you have to do this, you have to do that. That is also very important. That's the kind of thing that will differentiate one CV from another. So that, I think, was, those are maybe, two kind of experiences that are helpful to have as an undergraduate. Some independent research, some independent project experience doesn't necessarily have to be research, and demonstrate leadership skills in building something, running something, like you're doing. Technical skills are a requirement for success. Mm-hmm. I think if you have good communication skills, good personal management skills, things that are maybe harder to teach, that becomes a value, an augmentation. You'll drive your career faster with that. But you have to have that technical base. And very often when people do something significant technically early on in their lives, it just stays with them. It would be like a badge of honor. So this guy, he developed the first object editor that led to Photoshop. Even 30 years later, that's a nice badge of honor. If you have that technical accomplishment and demonstration early in your career, it tends to stay with you. Mm-hmm. So that's a prerequisite of a good technical skill set. The geeks will transform healthcare. Like they have everything else. That's what's going to happen. I'm not saying, the techies are going to do it. They will, like they've done everything else. And law will actually come to this also eventually, because you can code up law and you can calculate with it. Mm-hmm. But the cost pressures on the healthcare system are enormous and unsustainable, I think, as we all know. And the only way to deal with it, I think, are technical solutions. All these solutions associated with monitoring yourself, your habits, Google, the Apple Watch, things like that. I've carried these monitors around myself, trying them out. They affect your behavior because you just start to see data, how much you move, how much you eat, how long you sleep. And I think monitoring your basic variables like this is going to lead people to healthier habits. So I think that's one way of doing it. I think the analysis of medical information, medical IT is a huge field that will grow to be much bigger, I think, than bioengineering. That's why I'm encouraging this department to have an IT program here, so people will know bioengineering and IT. So just better management of healthcare records, better management of decision making, will improve efficiency in the system. I think monitors, sensors, devices will continue to be developed because you have to harvest all this information, collect it, analyzing, presenting it is useful. Then, of course, eventually it has to be interpreted, and that's where bioengineering type models of physiology, maybe all the way down to genetics, will become useful. So I think bioengineering, in a broader sense, and related fields, from a technical standpoint, will have a huge impact on medicine. And our Dean of Medicine here says himself that bioengineering is going to be more important to improving healthcare in the future, or will have this, I should say, he says, will have a similar role in improving medicine in the future as molecular biology has over the last 30 years. So I think it's a field of the future. Creative young people will see a lot of product opportunities, and I look to see some very successful graduates come back here over the next 10, 20 years.